Good morning. So in this video I'm going to demonstrate how to solve an application of related rates. You most likely saw that in the chapter that there was up to about 5 steps on how to solve a application of related rates problem, of which in most cases you're trying to find the given information, what's being asked, and the equations to be used. And of all these types of problems, you always want to draw a figure. But let's go ahead and just read through this. One airplane is approaching an airport from the north at 150 kilometers per hour. A second airplane approaches from the east at 274 kilometers per hour. Find the rate at which the distance between the planes changing when the southbound plane is 27 kilometers away from the airport and the westbound plane is 20 kilometers from the airport. Now, what I got from that is that we have one plane that's going south and one plane that is going west. So that means that we can model this by using a right triangle. So let's change the color. So we're going to draw a right triangle. Oops. Let's do that again. Okay. Now what we can do here is just label one of the sides as variable x. Oops. Variable x. And the other as variable y. Now we want to know about the distance between them both, so we can just change this to, or the hypotenuse, we'll just write z. Now, when we look at this equation, or this diagram, we have that the thing that we should think of when we look at right triangles is that we have Pythagorean theorem, which tells us that x squared plus y squared is equal to z squared. Now, the information of which that we were given was that the rate of change for the plane that's going south was 150 kilometers per hour. And we'll go ahead and include the units. Then we also have that the rate of change for the plane that's going west is going to be 274 kilometers per hour. So we have dy dt is equal to 274. And let me just try to squeeze in the units. Okay, but the thing that we don't know is how what the rate of change between the planes are. So that means that we actually don't know what dz dt is, and that's exactly what we're looking for. So looking at this, what we can do next is just take the derivative of the equation x squared plus y squared equals to z squared, but we're going to do that with respect to t, or time in that case. So that's not too bad. So we're going to go ahead and say that if we take the derivative with respect to time of x squared plus y squared, and we have dt equals to 2, not equals, but z squared. Now this is going to give you the following. It's going to give you 2x, but you want to tag on a dx dt plus 2y dy dt equals to 2z dz dt. Now, what I'm about to do is actually go ahead and say that, well, looking at this, we have that the 2's do cancel out, so we have that the 2's cancels out. But I can see easily that we can go ahead and just solve for dz dt, because if I divide by z, that will isolate dz dt, because we already know what x is, we know what dx dt is, we know what y is, and we know what dy dt is. So it's all just a matter of just substituting everything in. Now, one thing that I did bypass was that note that if you know what x and y is, that means that you know what z is. So z is actually equal to the square root of x squared plus y squared. So that's going to be key to reducing our computation, because we have that dz dt. If we go ahead and we just substitute everything in, we have that that's going to be, well, how far was the north southbound plane? It was 27, so we have 27 times 150 plus the 20 times the 274, and it's okay that my diagram is not to scale. Okay, and all of this is going to be divided by the square root of 27 squared plus 20 squared. Now, if we go ahead and we do that computation for what dz dt is, we should get that dz dt is approximately that's going to be 284 kilometers per hour. Okay, and we'll just go ahead and box this so that way we have our answer. Okay, and that's it really. So more or less, a lot of these problems go about the same process. You just try to find like a nice figure that that you can use. So like if you're talking about like a melting snowball, you know that it's a sphere. If you're talking about a heap of rubbish being crushed, then you know it's a cube. If we're talking about a right cylinder, well, in that case, you know, you're either using surface area or volume. Okay, so just be sure to review the different types of shapes and the different types of equations that might be used to relate the all the given information that you have in a typical word problem. Okay.